G'day guys, how you doing? This is the BARKER past paper we're doing, and this is the last multiple choice question that we've got. So it's from the Extension 1 Semester 1 paper, and the question is, it's actually probably the hardest question in the paper if you ask me, and it's one where there's like a very clever trick that you need to do, and unless you're like Stephen Hawking, you're probably not going to work it out why you're in there. So it's good to get a handle of this trick now. So the question is, the area bound by this curve y equals f of x, and the coordinate axes, so the x-axis, the y-axis, and this curve here, so just this shaded region, is rotated about the x-axis. So we rotate this shaded area about the x-axis, and the volume formed is v centimeters cubed. And I've drawn a picture over here of what you might expect to see. So this is the so you see this orange shaded area here that I've done. That orange shaded region is the same one as this shaded region here. So it goes into this shape, but I've only just drawn this bit because this will be the only bit that you could see in the picture. And we've rotated that bit around the x-axis, and we ended up with this green hemisphere on its side here. So this is the curve of y equals f of x, this one here. And they're saying if the area bound by y equals 3 times f of 2x, so not this anymore, and I'll show you down here what this might look like, this 3 times f of 2x, and the coordinate axis is rotated about the x-axis. What's its volume? So when the volume of this hemisphere is v, but if we do, instead of rotating this f of x curve, we rotate this one around it. How big is its volume in terms of, compared to what it would be if we just rotated this one around? So it's a very tricky question, and I've written down the method here of what we're going to do. But first of all, say this is the blue one. So the blue one is y equals f of x. So that's what we initially had, and when it was done in orange in the diagram above. Then, if that's the case, then the red one will be 3 times f of 2x. So it's half as wide, because that's what this 2 does. Here, it makes everything skinnier. But it's also 3 times higher than a, because, say this y value used to be a, we're timesing it by 3, and so it's going to, 3a. Beautiful. So what we're doing now, we're going to talk through this method. So the volume, so the first step we're going to talk about the volume for y equals f of x. We're going to write down a formula for that, or a formula for this here as well. And step 2, we're going to make some clever substitutions and then some clever rearranging. This is very vague, and then we're going to do something called the dummy variable step in step 4. So that's very vague. I don't expect you to know anything what that even means, but I'll talk you through it now. So the volume when y equals f of x, that's the original circle-looking thing, is revolved about the x-axis. But this is the formula we're going to get, right? But the new function, remember that complicated one that was like 3f of 2x? When we revolve that one around the x-axis, the v of new function stands for this one, the fancy function. The volume of the new function is going to be pi times the integral of, and now instead of f of x, we're going to have this, 3 times f of 2x, and that's all going to be squared. Very remember to make that all, we're going to square that whole thing dx. Beautiful. So this is the step, so that's the first step done. The second step is that clever substitution I talked about. So I've just rewritten the volume of the new function that we've got here. But I've put a 9 here, and the reason where that 9's come from is that this 3 here, we were squaring that, so we've got a 9, and then I've just taken the 9 out the front. So that's where that 9 comes from in the blue step. Now, and here I've just divided by 9. So I've got 1/9 v of the new function. Remember that this is the new fancy function we had, the volume of that. And then pi times the integral of f of 2x all squared. Now, here's where the clever substitution comes in. What we're going to do is, I'm going to say, and this is something that you'd probably have to have seen before you do it unless you're an absolute genius. I'd say, let u equal 2x. Alright? Now, you're like, okay, where's that coming from? How does that help? Alright? What we're going to do is, now I'm just quickly going to differentiate both sides. So I'll explain why I'm doing this in a minute. But we're going to get du dx equals 2. So therefore, we're going to get du equals 2 dx. Cool. And then, I'm just going to make dx the subject here, and I'll explain why I'm doing all this in a minute. So dx equals half times du. Beautiful. Now, why have I done that? Now what I'm going to do is I'm going to substitute. So I've made this substitution. I've let u equal 2x, right? And I've worked out what dx is in du is in terms of dx's, or dx in terms of du's. And I'm going to substitute that into this green equation that we've got here. So I'm going to write 1/9 times v of the new function. Remember, v of the new function is the volume we get when we rotate that new function. That weird, complicated looking thing. 3 times f of 2x about the x-axis. So that equals pi times, now, for 2x here, I'm just going to put, because 2x is u now. So I'm going to write f of u all squared. Beautiful. Now I could put dx here, but that would be a pain, because now this is in terms of u, and if we've got a dx on the end, it's a bit of a pain. So I want to put this du here. But so dx equals half du. So instead of this dx here, I'm going to put what we had just here, 1/2 du. So that's why I've bothered doing all this stuff. When earlier you were probably like, why are you differentiating both sides? What's all that about? I'll explain. So that's why we've done that. Now what I'm going to do is, there's a half here, so I'm just going to times both sides by 2. So that'll go, and then I'm just going to put a 2 here. So we're going to get 2/9 times the volume of this new function. Beautiful. Equals pi times the integral of f of u all squared du. Now that's step 2 done. So now I'm going to go on to step 3. Or that is step 3 as well. Sorry, that's 2 and 3 all done. Beautiful. Where did step 3? Step 3 came in when we started rearranging things. So I don't know. We'll just say step 3. Maybe I've buggered that up. But anyway, so we'll go to step 4 now. So step 4 is the dummy variable step. Now this is very contentious stuff. So step 4, I'm just going to write, I'll write down where we were. So we had 2/9 v of the new function equals pi times the integral of f of u squared du. Now, see if this makes any sense. So if we're going to integrate, a limit, say we're going to use a definite integral, we want to do the limit of 0 to 1 of x squared dx, right? We can integrate this function and then substitute our limits in, and we're going to get a number back. And it doesn't matter whether we use, in terms of x's, or whether we do it in terms, so u squared du. It's going to be the same thing. It doesn't matter what letter we use. We could use x or u or t, or you could use little pictures of elephants for a letter, like whatever it doesn't matter what symbol you're using, right? So this is where that dummy variable step comes in. So, all right, using x as a dummy variable, we could write, now this is, I'm going to rewrite this step up here. Oh, what have I done there? Sorry about that. I'm going to rewrite this step up here using the fact that it doesn't matter whether we use u's or x's or t's or whatever. So we're going to get 2/9 times v of the new function equals pi times the integral of f of x. So I'm not doing that. F of x squared dx. Right. Now, so I've just used the fact that it doesn't matter what letters we're using. We could use u's, we could use x's, we can use t's, we can use whatever, as long as we change everything consistently. Now, what is this? The integral of the pi times the integral of f of x squared dx. Remember from the top here we had the volume, which is this volume v, which is just the volume we get when we rotate just this one, not the fancy function, not that 3 times f of 2x thing, just this one. We're going to end up with this expression here. So pi times the integral of f of x all squared dx, that equals v. Right. So that's exactly what we've got down here. So I'm going to just substitute v in for here. Right, too easy. So we're going to get 2/9 times v of the new function equals v. Remember, v is the volume of just what you get when you revolve f of x around the x-axis. And then we're just going to times both sides by 9/2. So if we times by 9/2, that's going to cancel. We're going to get 1 here. So we've got to times the right-hand side by 9/2 as well. And we're going to get, so that'll cancel. We're going to get v of the new function. So that means the volume of this new function is 9v on 2. And hopefully, if we're not going to get really embarrassed, 9v on 2, beautiful. So it's B. So those are the steps we use. We worked out the volume for the new function, that we had this fancy function here, and then the main step really is this dummy variable step. So we made a clever substitution, so that u equals 2x. That was probably pretty pivotal. You probably had to have seen that before you do it. So remember that clever substitution, and then you've got to change your dx's and du's. For dx, you've got to pop in half du, and then what we did was we used the concept of dummy variables to work out what the volume of this new fancy function was. Alright guys, well that's the multiple choice done, and to be honest, that was one that I didn't get. I had to call up a mate to help me with that one, because it was tricky. So don't feel bad if you're like, oh, that was weird, but I hope I managed to do an alright job at explaining it to you, and I'll see you in the working out ones. Cheers guys.